All right, so I want to start by thanking the organizers for inviting me to come talk a little bit about some of the work we've been doing. So this project is part of Tox21 and is a cross-partner project collaboration between NTP and EPA. And so the point of this is to kind of figure out what happens to a chemical when you put it into an in vitro system. Where does that chemical actually go in the well? And so we actually like to call this project Where's Waldo? So we're trying to figure out where that chemical is. So why is this important? So when we do in vitro to in vivo extrapolation, there's a steady state assumption that's made, and where you're saying that the blood to tissue partitioning is approximately somewhat related to the cells to media partitioning. So if we think about an in vivo experiment, we have a daily dose. That daily dose, we can get a steady state concentration from that dose. So in an in vitro experiment, what we want to be able to do is to get a steady state concentration in that in vitro system and then relate that back to an oral equivalent daily dose. So currently IVE predictions rely on the nominal concentration. So the question becomes, what if that nominal concentration, the concentration that you're saying you're putting into a well, is not actually the concentration that you have in your cells? And the answer to that is that your prediction accuracy may be affected. So what we're trying to do here in this study is, so far, very few chemicals have been actually empirically evaluated to see where they kind of go in the system, where are they ending up. And we don't know to what degree that differential partitioning is going to affect IVE predictions across the Tox21 chemical library. So what factors can influence in vitro partitioning? So we look at this schematic of an in vitro system. So when you throw a chemical in a well, it can exist in the media. There's serum constituents in there, so your molecule can get bound up to some serum proteins. You can get your chemical stuck to the plastic of your well, or hopefully you're actually getting your chemical into your cells, which is where you want it to end up. So in 2014, Armitage and co-workers published this paper where they suggested that the in vitro partitioning relates strongly to KOW and to the concentration of the serum in the media, and that the absorption of plastic played a smaller role in determining the cellular concentration. So what we're trying to do with this project is to kind of develop the experimental data to further build upon these models so that we can better predict what happens in an in vitro system when we add a chemical to it. So, what are the things that are going to matter here? We know things like the amount of serum in the media is going to play a role. How much that compound is going to bind to the proteins in those serums are going to be important. The log KOW, and then finally the chemical binding to the plastic. So while what I'm talking about today is only a pilot of this project, I wanted to kind of go over what the whole goal of the project is and how we went about doing the chemical selection. So this project is going to be using 200 different chemicals. About 93% of those chemicals are in the ToxCast library. And we can see we have a mixture of about where half of them are low fraction unbound, 27% moderate, and 29% high. Most of the compounds are neutral at pH of 7.4, and then about 30% are anionic, and a smaller proportion are cationic. 60% of those compounds are inactive in the Adagene ER assay, whereas 4.5% were potent at 0.1 micromolar, and then 17.5% were potent at less than 10 micromolar. We did have some of these methods for some of these compounds already available at NTP, so that was kind of helped things out, so there wasn't as much method development that needed to be done. And if we really need to go back and check our methods, there's a few of these compounds that have some radiolabel compound that are available somewhere at EPA that we could kind of test things. So for these 200 chemicals that we're interested in looking at, we looked at the data from the Armitage model, And that predicted that the cells will be 100-fold lower in concentration when compared to the media for about 10% of these compounds. It'll be 3.2-fold lower than the media for about 15%. 18% are going to fall within 3.2-fold of the media. You're going to have 36% of these compounds where the concentration in the cell is greater than 3.2-fold of the media concentration. And then 18% of those compounds are going to be greater than 100 times the media concentration. So you can kind of see from these numbers, you know, what you think you put in the system might not actually be what you have going on, and it's why we think this is important to invest some time in this. So what are our goals of the project? First, this is a lot of samples, so we wanted to work and make sure that we were going to be able to handle all the sample generation and sample handling, make sure we know what we were doing there. Before we invest all this time, we want to make sure we're actually getting the information that we want from this. And from my point of view, being the analytical chemist that's working on this, I was interested in making the data collection process and analysis as efficient as possible, because as you'll see, it's a lot of samples. So here are the 10 chemicals that we selected out of that class of 200 compounds. And so these were all chosen because I knew that they would all ionize in positive mode in our mass spectrometer to kind of cut down on the number of runs that we would have to do for the pilot. But I did try to go through and pick out some kind of different functional groups on these compounds, so they all weren't identical. There were some, some differences there. So how about our study design? So we're looking at we're using MCF7 cells. In order to do these experiments, we actually use 9 different test plates. We have 4 technical replicates. For the pilot, we have the 10 chemicals. We're just using the 1 concentration. We have 3 time points, 1 hour, 6 hours, and 24 hours. And then 2 media concentrations, 1% and 10% FBS. So if you look at the plate matrix here, for each of the time points, we have 3 test plates. The first test plate just has media and chemical in it. There are no cells there. And from that test plate, we sample the media so we can get the media concentration. And then we crash what's left in the cell with what's left in the wells to give us the amount of chemical in the plastic. So then we take a test plate that has media plus the cells plus our chemical. We take off the media, we can again get a media concentration. If we look at what's left in the well, that gives us our plastic plus the cells, the amount of chemical there, which we can then use along with just our plastic compartment to figure out how much is in the cells. And then finally, to kind of tie everything together and get some mass balance, we do another test plate where we have the media plus the cells and the chemical, and we do a whole well crash. So how is all this sample design and generation actually done? Cells are plated with a peristaltic dispenser. Then we use an acoustic dispenser to put the chemical into the plate. We use the via flow to transfer the media from the test plates to the receiving plates. And then we have a micro dispenser that's where the acetonitrile gets added to crash the reactions. So for the analytical methods, we have a LC system that's a thermovanquish, and it's set up in combination with a thermo Q-exactive plus mass spectrometer. We set things up to have a 7-minute LC runtime, and that's done on reverse phase C18 column chromatography. Pretty basic mobile phases, with the mobile phase A being water with 0.1% formic acid, and then mobile phase B being acetonitrile with the formic acid. It's a gradient elution where we just increase from 10% to 100% B over 5 minutes, hold it at that 100% for a minute, and then bring it back down to the 10% to get ready for the next injection. As far as the running the mass spec goes, we've run everything here in targeted single ion monitoring mode, which basically means we're only looking for the chemical peak that we're interested in. So we're ignoring all the other stuff that's there. That helps us get better sensitivity in the end and helps make the run much faster. how do we go about actually calculating our concentrations and amounts? So in the media and whole well samples, in order to get our final concentration, we take the raw concentration, which is the information that comes out of our mass spectrometer. We then, there was the post-incubation dilution when we crashed the wells with acetonitrile, and then I did a further analytical dilution right before injecting the samples to get things into a good enough concentration rate, and then I wouldn't contaminate the instrument. If we're interested in calculating amounts, we just need to multiply that final concentration times the volume that's in the well. And then, so one of the big things we're interested in is, again, the concentration that's actually in the cells. And in order to get that, we're going to take the amount that we have in our well that has our plastic plus the. From that, we're going to subtract the amount that was bound to the plastic. And then we divide by our molecular weight times the volume of cells. And so for the volume of cells, this was done in 384 well plates. We used 10,000 cells per well. There was literature we went back and looked at and found that the volume of an MPF7 cell is about 2.0 picoliters. So the volume of cells is 20 nanoliters. And that turns out to be really important because when we're looking at the concentration of cells, we're talking about measuring something in 20 nanoliter volume. Whereas when we're looking at the amount that's in plastic, we're looking at like 60 microliters. It makes a big difference and has created some challenges. So now to some actual data. So the first thing that we wanted to look at is we wanted to compare how much chemical was in that whole well crash. And so what we did is we plotted the theoretical concentration on the y-axis, so how much we actually dosed into the well that we knew we put in there, and what we actually measured. And then we have this line here with the slope equal 1. So our theoretical and actual concentration should be equal to each other. So we would hope everything would land around that line. And for most of these cases, we did have an issue with rifampicin, and it was an issue all throughout all of these experiments. So we're in the process of trying to figure out what's the issue with rifampicin and why we are measuring significantly less than what we think we should be. So when we look at the concentration in the media versus what's in the whole well at the 24-hour time point, the first thing that may jump out when you look at this is that we don't see one of the bars here for acetaminophen. And so that's just a sample of the issue. So that's not actually real. We just haven't gone back and run that sample again to see. And the second thing to note here is if you look across here, consider the error bars that are associated with these measurements. Basically, the concentration that's in the media is pretty much equivalent to the concentration that's in the well, except for rifampicin, which we've kind of talked about is kind of weird. We don't know why yet. So now for the kind of big point here. So what's our concentration in our cells compared to the concentration in the media? So we see these really small orange bars here. That's the concentration that's in the media. So we know that should be about around 10 micromolar because that's what we dose the system with. So then if we look at the blue bars, which is the concentration in the cells, for the 8 out of 10 of these compounds that we can actually measure chemical in the cell, we see that we are getting an increase in the concentration by up to, in the case of triphenyl phosphate, almost 200 times that concentration that we actually think we're dosing at. So this could be pretty impactful, you know, when you start thinking about making decisions on how much of a chemical you're putting into a well. You're actually, you know, in some cases have a lot more that's getting into your cells. So to this point of how we're able to figure out the amount of chemical that's in our cells and comparing the amount that's in the plastic versus the amount that's in the plastic plus the cells well. So again, when we compare these, I have this slope of one line again. Basically, only things that fall below that line are things which we can actually measure the amount of chemical that's in the cell. And to give you an idea, we're talking about differences here of like 10 to 15 nanograms is how much is actually in the cell. So it's a very, very small amount that we're trying to measure. So the last thing we wanted to do with this pilot is we took our measured concentration data for the intercellular concentration, and we wanted to compare that to that Armitage model to see how that model looked like it performed. And so the answer is kind of okay. Like we do see, for some of these compounds, we are kind of hitting around about the same spot, model versus experimental. But then we do see some that are off way over here to the side. The goal here is, starting to generate the data so that we can, how do we make these models improved so that we better know when someone is putting a certain amount of chemical in an in vitro system, how much chemical is actually getting into their cells. So instead of a traditional conclusion slide, I will entice you guys to come talk to me at my poster, where I have the 6-hour time point data there. Also, I can talk to you about how we're handling the analytical demand using something called cassette analysis. We're basically running detecting multiple compounds at once instead of one at a time. And the reason for that is, in order to run this study for 200 chemicals, it was going to require something like 290 days, 24 hours a day of constant LCMS runtime. So we need to figure out a way to logistically do this. And then finally, we can talk about how this pilot study has informed our study design moving forward and how we hope to get better results from this. And with that, I'd like to thank all the people who have kind of helped make this work possible.